Welcome back to the third and final video of the 19th chapter of the Crystal Clear Electronics curriculum titled EEPROM Non-Volatile Memory. Together with József, we will show you how to use the EEPROM memory of the ATmega16A microcontroller. First, let's have a look at the datasheet of the device. See the ATmega16A datasheet on pages 18 to 23 for information and instructions on using the EEPROM. You can see the memory size, the access per byte, and the guaranteed 100,000 write and erase cycles. You can find detailed information on which registers to use and how to control them in order to read and write the EEPROM. There are three registers controlling the EEPROM: the EECR, EEPROM Control Register, the EEAR, EEPROM Address Register, and the EEDR, EEPROM Data Register. The first one stores the settings for the EEPROM and the current operation, which can be read or write. The second stores the memory address used, and the third is the data itself being written or read. I won't go into the detailed usage of these here, because ATmel Studio provides an EEPROM library that does all the hard work for us, and we can control the EEPROM through a few simple functions. The EEPROM read byte and EEPROM write byte functions are used to read or write a single byte, but there are variants ending in word, that is 16-bit dword, that is 32-bit float and block. In addition, there is an EEPROM update byte that only writes data if it differs from the stored data. The EEPROM update block function has three arguments: the memory address of the byte array in RAM, the starting address in EEPROM, and the length of the block. The method is used to copy the first n bytes of the byte array to the EEPROM region, starting from the given start address. However, it only modifies each byte of the EEPROM if the value in the byte array is different from the value stored in EEPROM. Let's demonstrate through a simple example how to store a few configuration parameters, 3 in our example, using the EEPROM. The status of the 3 parameters will be displayed by 3 LEDs and it will be adjustable by 3 buttons. We won't give them names, but they could be settings. For example, say the first is the parity bit enabled or not enabled, the second is the even or odd parity bit, and the third can mean that 1 or 2 stop bits are used. Of course, you can imagine anything else behind the buttons. Load the CE19-1 EEPROM project into ATmel Studio, open main.c, and look at the code. Set up the wiring in the heading of the main.c file, which is also shown in the wiring diagram here. Before uploading the code to the microcontroller, put a comment before every line with EEPROM write in it. If there is a mistake in the writing, one of the pins may float, which results in rapidly blinking LEDs and rapid writing of the EEPROM, which must be avoided. If the LEDs are working properly, then you can write the EEPROM memory safely.
Remember, floating means that the pin is not in a defined state, so not in logic high or low, but due to the electromagnetic interference from the environment, its voltage and therefore its state is continuously fluctuating.
The purpose of the program is to change the value of the stored parameter when the button is pressed, that is the state of the LED, lit or unlit. The first task we need to solve is to change the state of the LEDs if a button is pressed, so if they are lit, switch them off, and vice versa. As a first step, we declare constants for memory addresses storing the state of each LED, or in other words pointers. The value pointed to by the LED1 pointer will store the status of the first LED, that is on or off. The LED2 pointer points to the status of the second LED, and the LED 3 pointer will control LED 3. The EEPROM of ATmega16A microcontroller is 512 bytes long, so memory addresses can be between 0 and 511, or in hexadecimal numerical system 0x000 and 0x1ff. In the example, we address the first three memory addresses for simplicity, so 0, 1, 2. First, the program completes the initialization of inputs and outputs with the IOINIT function. If the value in the EEPROM is 0, the LED must be switched off, else it must be switched on. When running for the first time, the EEPROM usually contains an erased state, meaning it is filled with 0xFF, so all three LEDs will be on. After initialization, we read the three numbers stored in the EEPROM and set the LEDs accordingly. To read a byte, we use the EEPROM read byte function, which is a single argument that is the memory address we want to read, and returns the value of the byte. With this, the initialization part of our program is done, and the next part is the infinite loop where we read the state of the buttons. The TBI function returns the value of the specified input, while SBI sets the given output to logical high and CBI sets the output to logical low state. The system reacts to the three buttons separately, but in a similar way. The only difference in the rest of the code compared to the section above is the EEPROM address and the pins. We enter the first if when the button on PD4 gets pressed and pulled up to logic high.
We did not implement hardware debouncing for the push buttons, but we still want to avoid the negative effects of bouncing, for example unnecessarily writing the EEPROM at every edge, wearing it out. Instead, we have to implement debouncing in software. One way of doing this is to measure a time after which the bouncing is sure to be stopped, and then after detecting the first edge, make the microcontroller wait for that measured amount of time before continuing. This is done by the delay function, which waits for the amount of milliseconds passed to it as an argument.
After pressing the button, we must wait for it to be erased, because that is when a complete button press is completed. Then, we read back the value of our digital output and change it to its opposite, while also writing to the EEPROM. The EEPROM write byte function takes two arguments and has no return value, the first one being the memory address where we want to write, the second being the actual value. Now let's upload the program to the microcontroller and see how it works.
Okay, we're done.
We expect that pressing a button will change the state of its LED, so now I press the middle button and the middle LED should light up. If I press the button again, the LED will go out. Now let's see what happens if we press more than one button at the same time. I press the two edge buttons at the same time. You can see that only one of the lights is on, so this program can't handle more than one button at a time. Now, let's see if our EEPROM memory really works. Set a code combination, then disconnect the power to the circuit. You can see that the system is now powered off and the LEDs are off. As soon as I plug the power supply back, the same two LEDs should light up as before the power was off. You can see that this has happened, so we have managed to save our settings to the EEPROM.
As you can see, this example code can only handle one button press at a time. Try to implement the code that is capable of detecting all three buttons being pressed at the same time. Keep in mind that writing to the EEPROM is a relatively slow operation, and you can only access one memory address at once. We would like to emphasize again that until you have made sure that your circuit and your code is working as expected, it is a good idea to comment out all EEPROM operations and replace them with reading and writing regular variables. This can save your EEPROM memory from being worn out too early. If writing an EEPROM does not need to happen immediately, or the software does not guarantee the data to be saved will be different from the data already in the EEPROM, it is a good idea to use the EEPROM update functions instead of the EEPROM write functions.
Of course, there are other ways to solve this problem. For example, switches, opposed to buttons, retain their state mechanically, so when using them, there is no need to store the state electronically. Their drawback is, however, that we cannot modify their state electronically, for example by a message sent over a communication channel, while we can do so with values stored in EEPROM. On top of that, storing numbers with switches is cumbersome, as you can only assign one bit to each switch, meaning that you need 16 switches to store a 16-bit number. For example, in the case of simple, low-security remote controls or garage doors, the transmitter and receiver addresses are usually set with an 8-bit switch. But for more serious remote controls, such as a car key, a jump code solution is used. Here, not only is the continuously changing code itself stored separately by the key and the car, but the data needed to generate the corresponding code is also stored in EEPROM memory. So, for example, for a new ignition key, the key must first be paired with the car.
In Chapter 19 of the Crystal Clear Electronics curriculum, we introduce you to the basic features and usage of EEPROM and explore the uses of this type of memory. We encourage you to experiment, build, and use EEPROM or other non-volatile memory devices and exploit their potential. We hope that the knowledge gained here will be of great help to you. In the following videos, we'll also show you important and interesting things from the world of embedded systems, so stay tuned.
You can download the curriculum in PDF format from crystalclearelectronics.eu or in Hungarian from kristálytisztaelektronika.hu. You can find a mobile app for Android and iOS platforms under the same name. Follow us on Facebook for the latest news and see you soon in the next videos. Bye!
Bye!